Welcome back to the PLC Programming course. Chapter 3 of Module 1 is going to go over some basic electrical circuit theory. Module 1, Chapter 3, Basic Electrical Theory. Electron flow. Electron flow is the opposite of current. It is the flow of charged particles from the negative to the positive side of the source. Electric charge moves from the negative surplus side of the battery to the positive deficiency side. Now, through the rest of this section, Chapter 3, you're going to see several diagrams which were all found on various references on the internet. This particular chart, allaboutcircuits.com. The purpose of my course is not to be teaching electronic theory or electron theory. It's simply to state it and show you how it applies to a PLC. So all of these references are on here, and I'm not looking to redesign the wheel here. So moving on, we're going to go to the next chart here, which is Kirchhoff's voltage law. Kirchhoff's voltage law simply states that the sum of all the voltage drops around the loop is equal to 0. Basically, when you look at the value of the resistances and the voltage drop that happens across a resistance in a circuit, when the circuit completes, they need to be equal to 0. That is Kirchhoff's voltage law. The sum of the voltage drops in a circuit equals 0. Ohm's law. The current in a circuit is directly proportional to the voltage applied. Here on this chart, you can see Ohm's law is stated in several variations based on the algebra. E equals IR, as we all know, is Ohm's law. In PLCs, there are two power sources that are potentially used: DC, or direct current, and AC, alternating current. These are the references of both DC and AC. AC is sinusoidal, DC is steady state. When you're discussing direct current or alternating current, these two diagrams kind of show a general circuit, but when you're talking about DC, you're generally talking in PLC systems 0 to 32 volts DC, and in AC generally the 120 volt, possibly the 240 volt range. And then you have in AC systems, you've got to deal with whether you have single phase or three-phase power. In three phases, it's again another discussion and a whole nother part of being in this business is understanding what three-phase, single-phase, AC, DC, and all of that are functions and what their possible safety factors are, and understanding how to employ those voltages. If you do not understand that, then you need to get educated on that prior to trying to control a system with a PLC. In a sinusoidal AC 60 hertz or 60 cycles per second, basically it's broken up into 360 electrical degrees. You have a high at 90, crossing back over neutral at 180, a low at 270, and back to neutral at 360, and this process repeats 60 times a second. A DC square waveform for timing charts. Basically, no matter what your DC voltage is, 5 volts, 24 volts, 12 volts, you have that described as the amplitude. And in your DC square waveform, you have a transition point or a leading edge. You have the amount of time that the voltage is at that level. Then you have a dropping edge, or when the voltage is turning off, and then you will have this cycle again. Now, if this was in the case of an encoder, then let's say your encoder has 1,000 counts per revolution, then this square waveform would happen 1,000 times for every revolution of the shaft of the encoder. In a normal DC system, the steady state of 5, 12, 24 would just be a straight line. If you see ripples in that line, that's noise on your power lines, but basically it should just be steady state. Again, here's an encoder when we're talking about a DC square waveform, channel A, channel B. This would be a, doesn't matter what the resolution of the encoder is, you would have an A leading B by 90 degrees. And if B leads A, then you're going the other direction. You have an encoder truth table. Now here, you would have channel A be high, channel B is low. If state 2 is channel A and B are high, then you have state 3, which is low and high, and then state 4 is low, low. And by looking at this in a PLC, you can be able to tell what direction you're going, where you are in the phase of the encoder. Module 1 is now complete.